Okay, so we've got a calculus question here. We're going to try and integrate this function here, 2y prime squared minus 2k squared y squared plus 2 minus 4y cosine x with respect to x. And the parameters are from 0 to pi over 2. And we've got these parameters here, y pi over 2 equals 0 and y of 0 equals 2. These are our conditions here. Now we're going to try and find a function for y. So we've got y prime, y squared, a y and a cosine of x. So we're going to need multivariable calculus to try and solve this. So we can see that x is our independent variable and y prime, they are going to be our dependent variables. They're going to depend on x. So how are we going to go about finding a function for y? Well, first of all, we're going to find a way to try and get the Euler Lagrange equation and then see if we can solve for that using these conditions, and then hopefully that will give us some value for y. Okay, so there's a couple of ways we can go. On this method here in this video, I'm going to try the Gateaux differential. If you check the link in the below, I will show you how to go direct straight for the Euler Lagrange equation. Both ways work. This is the way I'm going to go for today. So Gateaux differential, first thing, we take our function a and we plug in for y plus epsilon h. So we write it like this. Actually, I'll do square brackets. A y plus epsilon h. So now, what we're going to do here now, wherever we see a y, we're going to plug in y plus epsilon h, and that includes the derivatives. So 0 to pi over 2, and then 2. Now the y prime, that will become y prime plus epsilon h prime, and still squared. The 2k squared y squared. So the 2k squared, that's going to be some constant multiple squared and then multiplied by 2. So this term won't apply for the 2k squared, but it will for the y. So minus 2k squared y plus epsilon h squared. The 2 is just a constant, so I'm just going to write that as it is. There's nothing to do here. And then my minus 4y cosine x. Now the cosine x is not included here, even though y is a function of x. So the y plus epsilon h only applies to this y. So I'm going to bring my cosine x with the 4 at the front, and then multiply that by y plus epsilon h. And then all of that is with regards to x. So that's the first stage for the Gateaux differential. Okay, next stage is we take the derivative with regards to epsilon, what's in the integrand. So we can do the derivative within the integrand. So I'm going to write this up here now. A of y plus epsilon h, 0 to pi over 2. Now I'm going to take the derivative inside the integrand. So the derivative of a with regards to epsilon, and then of all of this, so I'm going to write this up as 2y prime plus epsilon h prime squared minus 2k squared y plus epsilon h squared plus 2 minus 4 cosine of x y plus epsilon h, all with regards to x. So I'm going to take the derivative of this just to try and see where we are when we're taking the derivative. Okay, so next slide, this will just carry on down. Parameters stay the same. So now I'm going to take the derivative with regards to epsilon. So this one here, this is going to be the chain rule. So just as in single variable calculus, multiply by 2, drop the 2 down to 1, so that's now going to give me 4 at the front, and then y prime plus epsilon h prime. parallelogram comes to 1. And now the derivative of the inside with regards to epsilon gives me h prime. This time we don't have the derivative of y or h, so this time the chain rule still applies, but it's going to be very similar but without the derivatives. So that's 4k squared y plus epsilon h, and then the derivative with epsilon is h. Okay, derivative of this with regards to epsilon is 0, that's just a constant, so that disappears. And now we're on to this one. So with regards to epsilon, the 4 cosine x is treated as a constant multiple. So we'll just write that in again. And then the derivative here with regards to epsilon, now the y, that will disappear. There's no epsilon there. But the epsilon h will now just leave me with h. Okay, and then we've still got the integration to do with regards to x. Okay, now the next stage is we take the limit as epsilon approaches 0. So that is also done in the integrand. So we've not done any integration at all yet, it's all literally just algebra. So wherever there's an epsilon, it's then going to give us a 0. So just marking these up, that will be 0, that will be 0, and there's no epsilon here, so there's no limit to 0 there, it just stays as it is. So taking care of this one, we've got 4y prime, this disappears and it leaves us with a h prime. So that's 4y prime h prime. It's a very similar story again here, 4k squared y, this disappears and it leaves me with h. So minus 4k squared and then yh. And then this one, we're just going to rewrite that because there's no limit there with regards to epsilon. Okay, right, so we could now submit this as our Gateaux differential, but we're still not really anywhere closer to solving for y because we've got this h prime here. Now calculus of variations, we want to try and get this in terms of h. So we need to do something with this one. So I'm just going to write this integral separately and leave these out of the next stage, because I could, if I wanted to, split this integral into 3 different integrals. But I'm just trying to take care of this one and then plug everything back in and see where we get to. So what we could do is, if I just bring this out to here, so from 0 to pi over 2, I've got 4y prime h prime with regards to x. So to take care of this, to try and get this in terms of h, we're going to need integration by parts. So integration by parts, basically the formula for that is the integral of u dv, so u and the derivative of v, just write that v a little bit neater, equals uv minus the integral of v and the derivative of u. So using this formula, we need to choose a h prime to be either the u or the dv. Now, for the h prime to turn into a h, we need to integrate this derivative out just to get us to h. So therefore the dv needs to be our h prime. So therefore our u is our y prime. So I'm just going to write this under here just to help us with that. And then we just go to the formula. Okay, so the integral here with regards to integration by parts. Now uv is part of our answer. So u is the y prime. Our v will be the integral of h prime, which is h. And that's from 0 to pi over 2. And then minus another integral, same parameters, and then v and du. So v is going to be h, and our derivative of u is now going to be y double prime. So I'm going to write this as y double prime h dx. So that's us now integrating this and getting this h, but we've still got our y prime h here evaluated at 0 to pi over 2. Now, as this here is an admissible function, we're going to try and find the stationary path. Our h of 0 and our h of pi over 2 are both going to be 0. So if I just write that here, h of 0 equals 0, and our h of pi over 2 is also 0. So therefore this term is now going to disappear, and then we're just left with this integral in place of this. So now what I can do is I can just rewrite this integral. Instead of this, I can now write this in its place. Okay, so we've got this far now with our Gateaux differential. Now I'm just going to rewrite it now, because this next stage is going to help us. If I factor out this h and rewrite the function with h factored out. So our Gateaux differential, which is, we can write like this, from 0 to pi over 2, and then I've got minus 4, minus 4, minus 4. So I'm going to bring that minus 4 out to the front. And then continue here now with this factorisation without the h. So I've got y double prime. So I've got my minus 4. The h I'm going to write on the end here. My minus 4k squared is now just going to be minus k squared. But the minus here will now render this as a plus. So that's plus k squared. And I need my y here as well. H I'm going to come to. And now a minus 4 here, which will now render this into a plus again. So plus cosine of x, all in brackets, and then my h, and then dx. Okay, so as we're doing calculus of variations and we're trying to find a stationary path, this Gateaux differential should be set to 0. So therefore what we have is, by the fundamental lemma of calculus of variations, this should be 0. Now, inside 0 to pi over 2, h is not necessarily 0. We don't know anything about it. So the only way we could have a 0 is if we set this to 0. So therefore, by the fundamental lemma of calculus of variations, by the fundamental lemma, I'm going to just write this out. Of calculus of variations, we are left with y double prime plus k squared y plus cosine of x equals 0. That's got to be our stationary path.